Continue on. Chapter 10 continues on in a similar order to Chapter 9, so we'll see a lot of the same reactions we saw with alkenes. The next one we're going to look at is hydrohalogenation. So let's do this as a comparison to Chapter 9. So with hydrohalogenation, that was when we added something like HBr to an alkene. And which side of the alkene will the bromine get added to? More substituted side. We always go through the more stable carbocation. I'm not going to show the full mechanism. If we wanted to get it attached to that anti-Markovnikov side, what would we add? Peroxides. It's similar with alkynes, however, there's a little bit of a trick. With alkynes, we can have this pi bond attack HBr. And we could say, we're going to attack this proton, kick off our bromine, and maybe we'll observe something like this, where bromide attacks back in, and we get our final product where our bromine's attached to an alkene. Unfortunately, this isn't what happens. This is called a vinylic carbocation. Is not observed. And so the reaction actually does not proceed through this mechanism. It proceeds through a variant of this, and it's a little bit debatable exactly how it occurs, but one thing I will show you guys is they were able to determine it wasn't this mechanism by doing a rate experiment. They determined that the rate was equal to some rate constant times our concentration of our alkyne times our concentration of HBr squared. So is this a first, second, or third order reaction? Third order, right? So we would add the exponents together, that 1 plus 2, it would be a third order reaction. The mechanism I have drawn above is what order? First order, right? It relies on the collision of one HBr molecule with one alkyne. The rate experiment says it's not just one equivalent of HBr that's important, it's actually the collision of two equivalents of HBr with alkyne that's important for that rate determining step. So the commonly accepted hypothesis, although it's a little bit hard to prove, is that it goes through this third order mechanism. Where you have some alkyne, and I'm going to draw in all my carbons just so we can keep track. And you've got two equivalents of HBr. You've got one above, and you've got one below. And they think this pi bond does attack one of these protons and kick off the bromine. However, one of these bromines gets covalently bound to the other carbon in this concerted termolecular process. So let's take a look at this transition state. I think this is really interesting. Maybe it's because I'm a nerd. But you almost never see these termolecular transition states because entropically it's really disfavorable to have three molecules colliding in space, right? So this is kind of an oddball reaction. So in the transition state, we're in the process of making not one bonds, not two bonds, 3, 4, actually 5 bonds are in the process of being made and broken in this transition state. Yep?
Because you'd have to have 3 molecules colliding perfectly at the same time, is this really accepted or is this pretty strongly? Is there like another competing theory for this?
That's a good question. So anytime I show you a mechanism, it's that nobody has disproved it yet, but we can never prove a mechanism absolutely exists.
So they'd have to be in space, and that's a linear molecule, so they'd have to collide perfectly for this to happen.
Yeah, it is a weird thing to think about, but the best idea we have at this point in time is that this is the most reasonable mechanism, but we don't have definitive evidence that this occurs.
Okay.
Yeah. So, yeah.
What happens to the hydrogen on the bottom left that is essentially losing the bromine?
It's getting deprotonated or transferred to another molecule. Yeah, it's a little bit weird.
So there's no explanation about it sort of getting left behind, but
Essentially, yeah.
I think of those as getting pulled from things. Okay.
Yeah, it's one of these reactions where I kind of scratch my head at it still, but we do know that it's a third order reaction. So if we look at our final product, we end up forming a new alkene. And the bromine still comes off of the more substituted carbon. So we do get that same product from the first reaction. We just know that the other reaction is a little bit different. And then the byproduct of this reaction is going to be HBr. So in that top portion, you're kicking off a bromide and a proton's left behind, so you're getting that HBr as a byproduct. Yeah. All right, let's take a look at this in a little bit more detail. And this reaction is actually somewhat reversible. So let's say we've got this alkyne. And we add in HBr. And typically this reaction is done in excess amounts of HBr. We want to push it. So when we do this, we'll brominate it once. However, this is really, really hard, if possible at all, to isolate. So typically, you don't isolate this compound. What do you think happens if we have excess HBr? Yeah, it keeps going, right? We've got an alkene. We know alkenes can do another addition reaction with HBr. And if you do this, you end up forming a dihalide where you've got both bromines coming off of that same carbon. And then hypothetically, how can I go straight back to my alkyne? Yeah, a base, right? So we could do a double elimination reaction. So do an E2 times 2. What base would be good? Do you think hydroxide would be good enough? No, we've got to amp it up a little bit more. So typically with these reactions, you have to use a super strong base. And the most common one that's used with alkynes is sodium amide. It's NaNH2. And you typically use this in excess. And then just like I said yesterday, oftentimes you add in an excess amount of base, but then you run into the problem of deprotonating that proton coming off the end here. So you want to add that back on. And so your last step is reacting this with water to quench your reaction and get that proton put back on. So a lot of these reactions are kind of neat because you can add halogens on and you can take them back off. And remember that if both halogens are coming off the same carbon, this is referred to as a geminal dihalide. All right. So the question is, we just did a Markovnikov addition. Can we do anti-Markovnikov? Yeah, we can try for sure. So let's take a look. And with anti-Markovnikov addition with alkenes, what was the key feature that we needed? Peroxides. So with alkenes, we said if we want to add the bromine to the opposite side, we need HBr and some sort of peroxides. With alkynes, it's very similar. You can take an alkyne, such as this one. You can react it with HBr and some peroxides, and you get an analogous reaction. However, you actually get two different products out. You get one product where the bromine's sticking up and the other one where it's pointed down. What's the relationship between these? Yeah, you end up with a pair of diastereomers. If we look at this one on the left, is that an E or a Z alkene? It's an E alkene, right? So this would be our E isomer. And then what about the one on the right? It's got to be Z same side. So with these reactions, you don't have that much control over which one you get. Typically, you get a little bit more of the E because sterically, the groups are pointed away from each other. However, you typically get a mixture of products out of this reaction. This is similar to the alkene mechanism, and it goes through a radical mechanism. Does anybody know what a radical means in organic chemistry? Yeah, a radical means instead of moving pairs of electrons, we actually move individual electrons. We haven't covered that yet, but we'll cover it in chapter 11. All right, so now let's move on. In the alkene chapter, we did hydrohalogenation, and then we also did acid catalyzed hydration. So let's take a look if we can do that with alkenes, or alkynes as well as alkenes. So with alkenes, let's say I want to add an alcohol to the more substituted side. What reagents should I be using? Got two options.
Plus and water.
Yeah, H plus and water. What's a good acid that I could use for this? Yeah, sulfuric, phosphoric, one of those super duper strong acids that's non-nucleophilic, because you don't want your conjugate base to add into that carbocation. So typically H plus is sulfuric acid. In the textbook, they normally just write H plus. Makes it simple. What's another way of doing this reaction? Instead of using water and acid. Assume you hate the environment. Yeah, oxymercuration, demercuration, right? So if you want to avoid rearrangement chemistry, you can use the mercuric acetate. However, this is a much greener reaction, and it's typically the one that's preferred.
Probably cheaper as well.
Yeah, it's a lot cheaper. You don't have to worry about accidentally killing your chemists.
Oops.
It's just a chemist. They're cheap, right? Let's try doing this with an alkyne. So we'll take acid and H2O. Problem is that there is no reaction.
Never easy.
Yep, it's never that easy. The reason for this is that your activation energy is too large. So what can we use as a way of avoiding large activation energies? Yeah, some sort of catalyst. Typically, when chemists do this, they go out and they screen hundreds, if not thousands, of catalysts to find one that worked. There was actually a book I read a couple years ago called The Alchemy of Air, talking about the development of some catalysts. And I'm not even kidding. They tested like 10,000 catalysts. So oftentimes it's a screening process trying to find some catalyst that works. And the catalyst that works well with this one is another environmentally unfriendly catalyst. They still use acid, so sulfuric acid, phosphoric acid, usually sulfuric, and water. But now we use another mercury compound.
Mercury's just a problem.
Yep. So this is our catalyst. This will lower our activation energy. And so then the question is, well, are we going to add an alcohol to this blue side or to this red side? The blue side, right? Just like before, we're going to add it to the more substituted side. So when we do this, we could say, you know, it would make sense that we'll have our alcohol here, and then we'll have two hydrogens added on right here. This is a really special compound. This is an alkene and an alcohol mushed together. So chemists like to refer to this as an ene-all. The ene referring to the alkene portion and the all referring to the alcohol. So ene-all. Okay, these enols typically aren't very stable on their own. You can't stop at this step. It'll continue doing some unique chemistry. So let's take a look at the chemistry it does. And this chemistry is all in equilibrium. And in this reaction, we've got a bunch of acid around. And we typically have excess water. So let's try to come up with a decent mechanism. So what do you guys think might happen if we've got an alkene and acid around? Yeah, we're going to protonate the alkene. So then the question becomes, which carbon will carry the positive charge? So I'll give you guys a minute to think about this, but let's try to come up with both options. And then once you think you got it, check with your neighbor, and I'll draw out both options. Let me slide this over. All right, how many of you guys think you've got a solid hypothesis? Give you guys a hint. This is super similar to the quiz. Right? This one's not only super unhappy because it's primary, but this one has resonance stabilization, right? That carbocation's on the more substituted carbon and it's resonance stabilized. So I'm just going to cross out this other one because that's nonsense. And we're going to draw our resonance contributor, and we know, hey, this lone pair can donate down. And when we do this, we have a really similar molecule, but the pi bond's now in a different location. All right, now going back to first term, which one's our major contributor? Why do you guys think the one on the left?
Full valence.
Yeah, it's got full octets, right? So the number one rule we look for when we're looking at major and minor contributors is we know our major contributor is usually going to be the one that has full octets. So this would be our major. And this one would be our minor. So really that oxygen-carbon bond has more double bond-like character than single bond-like character. And then we've got water floating around. Oop. And this water can do a proton transfer and pluck off a proton from up top. What functional group have we made? Ketone. So really this reaction goes from an enol, that alkene with the alcohol, all the way to a ketone. This is referred to as a keto-enol tautomerization. So then the question is, what does tautomerization mean? Yeah, just moving a hydrogen around on a molecule through a bunch of different steps and ultimately changing the functional group as a result of that. So really we've done nothing but move protons around during this whole transformation. The key thing to remember with these equilibrium reactions is that the ketone is almost always favored. The enol is present maybe in 1% in equilibrium. The ketone's favored in 99%. So usually the equilibrium is greater than 90% ketone, less than 10% enol. However, that does depend a lot on the other functional groups that are attached. So this can vary a little bit. And we're going to see this reaction a lot throughout the year. So this keto-enol tautomerization will show up again and again and again and again. Your pod, if you look at it, is a keto-enol keto tautomerization. So you're going to be moving a lot of protons around. Remember, these equilibrium reactions can go backwards and forwards, right? So you can go from a ketone to your enol, or your enol to your ketone, or back and forth 3 times. It really doesn't matter. All you're doing is shuffling a proton around, and I want you guys to practice that with your pod. So let's take a look at some example reactions with this. And for this one, I want you guys to work through the mechanism. However, you can jump straight ahead to the enol. So we know in this mechanism we typically have H2SO4, we have water, and then we've got our catalyst. So let's go ahead, jump to our enol, and then I want you guys to push arrows and show movement of the protons and ultimately your final product. So I'll give you guys a minute to work on this.
Do we have to show that CH3 for those? Like,
You don't have to.
is there an extra method coming off, or that is a...
No, if you draw it this way or if you remove them, it's the same compound.
All right.
Yeah.
That's what I was wondering.
That's why I'm not-
And then for extra credit, not really, but kind of, let's name this alkyne. Mm.
Did we talk about female weights at some point?
Yes.
Is that
In fact, we'll talk about that next.
something?
3,3-dimethyl 1-butane.
Well, let's do the naming really quick. So do I want to number left to right or right to left?
Left or right?
Left to right, right? Just like with alkenes, we want to have the alkyne in the lowest position. So we know it's going to be a butane analog, right? So in this case, we've got a 3,3-dimethyl. And what goes next?
1-butane.
Yeah, 1-butane. Oftentimes with these, you don't even have to include the 1 because it's implied that its only option is to be in that 1 position, so you can even omit the 1-butane if you want and just say 3,3-dimethylbutane. Okay, so let's determine where the alcohol lands. Is it going to be on that blue carbon or the red carbon?
Red.
Red carbon. It's going to be on the more substituted side. So we know we've got 2 hydrogens here. We've got our alcohol. And then over here we've got this tert-butyl group kind of dangling off. This we said was our enol. And then in the next step, I'm not going to do, or I guess I'll do equilibrium arrows, just for consistency's sake. We've got our acid. What's next?
Double bond protein.
Yeah, we know our alkene, just like we saw last chapter, is going to grab this proton, kick it off, and we know that we're going to form the resonance stabilized carbocation. So let's go ahead and do that. Got 3 hydrogens on this other side now. And just like we saw in the previous example, this pi bond is actually getting dumped down, or the lone pair is getting dumped down and forming more of a pi bond. And remember, anytime you do resonance structures, not to forget your brackets and the double-headed arrow.
Why is it that the alkene is attacking the water as opposed to
That's
the
That's a good question. So the reality is, in equilibrium, some of that alcohol could be protonated. However, that doesn't really get you going in a forward direction. So it's kind of a dead end part of the equilibrium. This keto-enol tautomerization is the driving force. You're going to primarily go to that ketone. And then in this last step, we know we've got this proton transfer. Where this water molecule can grab a proton and give us our final ketone. What do you notice about the acid for this reaction? We had to have acid protonate our alkene. Yeah, it's regenerated, right? So in this reaction, the acid is catalytic. In fact, this keto-enol tautomerization will even occur without acid. It's just a lot slower because we know water itself is a weak enough acid and it will actually still push it to the keto form. However, if you add even a pin drop of acid, this reaction will speed up like 10,000 fold and really favor the keto form. So the acid is catalytic, you don't need much, and it really favors the ketone side of the equilibrium.
So there's 2 catalysts?
Well, the first catalyst, the mercury, is used for that initial hydration of your alkyne, and then any extra acid around is a catalyst for the keto-enol tautomerization. So yeah, there are 2 separate catalysts for this overall transformation.
But, there's no hydrogen on that as before, it's H2.
Yeah. So let's take a look at another reaction, this time a little bit harder. And you guys don't have to show the full mechanism, because your hands are probably cramping up. So this time we've got an internal alkyne, meaning the double bonds between 2 other carbons. It doesn't have a proton coming off one of the carbons. Let's determine what product or products we might get out. So I'll make this one worth 4 points. And then I'll do another one down here. You already lost 4 points? It's not a good way to start. And then down here we'll do a similar one. Also worth 4 points. And try to discuss with your neighbor what you think happens. All right, give me a thumbs up if you feel pretty confident in your answer.
For one, both of them.
For both of them. Couple thumbs.
Why did you put two benzene rings? Why?
It was for fun.
When you did one stereo set, you didn't have to draw two products.
Oh, don't get me wrong, they're fun molecules, they're just not fun to draw.
I'm going to color code this again just because I like to. I'm going to put a red carbon here and a blue carbon over here, and then same thing down here. So we saw in the above examples that the ketone ultimately goes to the more substituted side, right? In this case, which side's more substituted? Yeah, they're equally substituted, right? So in this case, internal alkynes don't have a more substituted side, right? They're both covalently bound to one other carbon. So let's draw an option. One where the ketone's coming off of that blue position. And we know that this is still 1, 2, 3, 4, 5 carbons long. So when I do these problems, typically what I do is I draw out my carbon backbone. And I number it, and I say 1, 2, 3, 4, 5. We know that our ketone's coming off the 2 position, so I'm just going to go ahead and draw this guy in. So that's one product. The other product we could do is the same one. However, this time we're going to do it where it's coming off the 3 position. And our double bond to oxygen is going to be there. What's the relationship between these? Yeah, constitutional isomers. These aren't diastereomers, they're not enantiomers, they're arranged completely differently. So this will give you a mixture of constitutional isomers out of it. This is one big problem with hydration of alkynes, is that if they are unsymmetric internal alkynes, you end up with different products. So let's try doing the next one. In the next one, do you think you're going to get one product or 2 products?
One.
Ah. So let's try it. We'll do one in blue, kind of like we did before. And we know our double bond's going to be where that blue dot is. And then over here, we're going to do the same thing. You guys are going to get good at drawing benzene rings by the end of this year. And the other one's where our double bond's coming off that red carbon. What's the relationship between these?
Yeah.
They're identical, right? So in this case, these are the same. They are identical. These ones are constitutional isomers.
What's the amount that you get into? Is it what, 50/50 or is one favorite?
I believe the book says you typically get a 50-50 mixture, but I'm sure that there are some situations where you wouldn't. So let's make a note of this, that you have to be careful anytime you have unsymmetric internal alkynes. With unsymmetric alkynes, you will get 2 different products. And I guess I should say unsymmetric internal alkynes, meaning that the alkyne is between 2 adjacent carbon atoms. Does that make sense? So in each of these, we were doing Markovnikov hydration, which leads us to the question, well, what if we want the anti-Markovnikov product? There's a way. So let's do a little review of our alkenes. And I think we'll have time to briefly go through this, but we'll do the mechanism in more detail tomorrow. With our alkenes, what reagents do we need if we want the alcohol to go on that anti-Markovnikov position?
Or B.
So BH3THF, and then number 2.
NaOH,
Yeah, sodium hydroxide, hydrogen peroxide. We know that that always favors our anti-Markovnikov addition. With alkynes,
You forgot,
oh, thank you, H2O2. And then with alkynes, we need to do something similar. And if we do this, you can imagine we're going to get an enol, but this time our alcohol is going to come off the less substituted side. So I'm going to put in my hydrogens just so we have a complete picture here. And this is our enol. And then when we do this, we're going to have to use a similar reagent to the one we used in the alkene situation. However, we've got to bulk it up. We're going to use a borane on steroids, R2BH. And I'll go through a couple of examples of these bulked up boranes. And then in step 2, it's really similar. You're going to use H2O2 and sodium hydroxide. And then ultimately, what do you think is going to happen with this enol? Yeah, it's going to make an aldehyde, right? So we saw in the previous example that this bond turned into a double bond, and the alkene turned into a single bond, right? So ultimately what ends up happening with these, and we'll cover this mechanism in more detail tomorrow, is you end up forming an aldehyde.
That's only because it was a hydrogen attached, not because of the boron.
That's a good point. So you're saying if we had an internal alkyne with carbons coming off of both sides, we'd form a ketone. But if that were the case, why would we be trying to do anti-Markovnikov addition, right? It's one of those catch-22s, right? So typically only see this reaction, this anti-Markovnikov reaction, with alkynes that have a proton coming on the end. Okay, so let's take a look at some common boranes that are used. So let me actually change colors so you guys can see it better. So examples of R2BH. Oop. The first one looks pretty funky. This is called diisamyl borane. And you can tell that this has these big sterically blocking groups hanging off of each end. In this case, why do you think we're bulking it up so much? What do you think BH3 could do with our enol? It could actually react again, right? We've got pi bond character in our enol. When we add on these giant groups, it can only attack with the alkene, or sorry, with the alkyne. It can't react with the alkene. So in this case, let's make a little note of this. They're too bulky to add to the second pi bond. So we have to add in these giant groups onto them. The second one is even trickier to draw. Oh man, let's see if I can do it on the first try. Hang in there. And we've, oh man, I already messed it up. And we've got a hydrogen going through here. Let me actually bold these so you can see where all the carbons are. I'm not the best at drawing some of these funky bicyclic bridges. But this is referred to as 9-bora bicyclo. And then what goes in the bridgehead brackets? It'd actually be 331 because we do have a bridgehead for that last one. So this would be 9-bora bicyclo 331 nonane. This is a mouthful and a half. So what most chemists end up calling this is 9-BBN. Sounds like a Star Wars character. Same situation as before. We've got these big sterically blocking groups so that it can only add to one of the pi bonds, not both of the pi bonds in your alkyne, and it just stops there. I think we're going to stop at this point. Tomorrow when we come in, we'll talk a little bit more about that tautomerization between the enol and the aldehyde. But try to get started on the pod early and try to work on it with friends too. Bounce ideas off of each other and make sure that you're on the right track.